Hi everybody, today we're going to talk about the dehydration of alcohols. Specifically, this week's experiment is going to involve the dehydration of cyclohexanol to afford cyclohexene. Okay, the dehydration of cyclohexanol to cyclohexene can be accomplished by heating with an acid catalyst. And the procedure that we've selected for you for this experiment involves catalysis by phosphoric acid containing a little sulfuric acid. Phosphoric acid by itself takes a long time because it's a weak acid, and sulfuric acid by itself causes charring and liberation of sulfur dioxide fumes. So when a mixture of cyclohexanol and acid catalyst is heated in a flask equipped with a fractionating column, which is the way we're going to do this, the formation of water becomes evident. On further heating, the water and the cyclohexene formed distilled together by the principle of steam distillation, which we learned about last week, and any high boiling cyclohexanol that may volatilize is returned to the flask. However, after the dehydration is complete and the bulk of the product has distilled, the column still remains saturated with water cyclohexene, that is, water and our product, and that merely refluxes and doesn't distill over. So to recover otherwise a lost reaction product, what we do is add what we call a chaser solvent and continue the distillation. The chaser solvent that we're going to use is water immiscible technical grade xylene, which has a high boiling point of about 140 degrees. As it steam distills, it's going to carry over the more volatile, relatively more volatile cyclohexene. So when the total water insoluble layer is separated, dried, and redistilled to the dried column, the chaser again will drive the cyclohexene from the column. The difference in boiling points is such that a sharp separation is indeed possible. So the holdup in the metal sponge pack column is so great that if a chaser solvent isn't used in the procedure, the yield will be only about a third of that reported in the literature. Okay, so the mechanism of the reaction involves three steps. A fast step is protonation of the hydroxyl, and a slow step is the formation of a carbocation via loss of water, and then there's another rapid step involving alkene formation. Okay, and you should know this mechanism from organic lecture and see that this mechanism is in the context of others. For instance, is this an E1 or E2 mechanism? Can alcohol dehydrations occur via E2 mechanisms? If so, what's required for E2? And when would E2 occur exclusively? Under what conditions? And why is elimination favored over substitution in these dehydration reactions? And do you think rearrangements might ever be a concern if we had, for instance, a different alcohol substrate? Okay. What you should do to understand how to set up your apparatus and use these principles involving distillation during the reaction is to watch our demo at our ChemPDX YouTube site, which is shown here, and watch the demo, download the demo entitled Dehydration of Cyclohexanol. Okay, enjoy your experiment.